Hi, everyone. I'm Gwangsun from the Federal System Architecture Laboratory at PostTech. Thank you all for joining us for this PyTorchSim tutorial. I think you already know what PyTorchSim is roughly at the high level. It is a simulation framework for modeling MPU architecture and compiler. In our research group, we are actively using PyTorchSim for research related to AI systems. So I hope you find it useful through this tutorial as well. This tutorial has 3 parts. In the first part, I will be providing introduction and overview of PyTorchSim. Then we are going to have 2 hands-on sessions for the basic usage and the internals, as well as how to extend PyTorchSim for your own research. So let's get started with part 1. As you know, the AI models are evolving rapidly, and they are also growing in size. So the computational demands from the AI models is increasing exponentially. So for example, the compute requirement of training AI models is increasing at a rate of about 4.4x per year. In contrast, the computational capability of hardware accelerators such as MPUs or GPUs is improving at about 1.4x per year. That's still fast, but not fast enough to keep up with the demands from the AI models. So there is a growing gap between the compute requirements from AI models and the hardware capabilities. And closing this gap is important for developing future AI models and deploying them. So there has been tremendous efforts to close this gap. And one of the prominent example is designing neural processing units or NPUs. So they are designed to accelerate AI workloads using efficient data flow units such as systolic arrays. And for example, so Google has been developing their TPUs or tensor processing units for more than a decade, and it's now at the 8th generation. And other big tech companies like AWS and Intel, as well as startups like Furiosa and Rebellions, are also actively designing their own NPUs. However, in designing future NPUs, it is essential to have a good modeling tool such that you can evaluate the performance of the new design ideas before actually implementing them in the RTL, which is very costly. So ideally, you will want a tool that's very fast and very accurate, but in reality, there is a trade-off between the two requirements. So you tend to use different set of tools across the different stages of the MPU or processor design process. So in the early stages, you'll need to explore a very large design space. And because of the larger size of the design space, you'll need to use a tool that is very fast, even if it sacrifices accuracy. So if you plot the level of abstraction or inaccuracy on the x-axis and the speed of the tool on the y-axis, such a tool will be placed in the upper right corner of the graph, as shown here. Afterwards, later when you have narrowed down the design choices into a smaller number of designs, you'll need to evaluate their performance accurately, even if you have to sacrifice speed. So such tools will be placed in the lower left corner of the plot. But because the speed of such a tool is very important for achieving high productivity during the design process, we want to achieve as fast a speed as possible while still preserving accuracy. That is the goal of PyTorchSim. So PyTorchSim strives to provide cycle-accurate simulation model that can model MPUs accurately while providing as much speed as possible. However, there are several challenges in meeting these requirements. First of all, the AI models are very diverse, and it's becoming more and more diverse. So even within the transformer architecture family, the attention mechanism can be implemented in very different ways. In addition, the feed-forward networks can be implemented in many different ways, including the mixture of experts model. And beyond the transformers, there are other model families like the diffusion models and state space models like Mamba. So the AI model landscape is becoming more and more diverse. So it is important to support many different AI models in the simulation framework. In addition, the NPUs are used for both inference and training. So it is important to support both phases by the simulation framework. Furthermore, many different operations are continually being introduced in the AI models to achieve good accuracy. Many of these operations are based on vector operations. So it is important to support comprehensive support for vector operations in the simulation framework. Also, as the models are getting bigger and bigger, sparsity is widely exploited to perform inferences efficiently. And mixture of experts model is one example of exploiting sparsity. So such features have to be properly evaluated. But what is challenging here is that the execution latency of the model can vary with the value of the data. In other words, we have data-dependent timing behavior. So such property has to be accurately modeled. When it comes to the NPU hardware, different components in the NPU need to be modeled accurately as well. So modern NPU architecture has units such as matrix multiply unit, vector and scalar units for computation, and the scratchpad memory to hold the data needed by the functional units, and the DMA engine that supports data movement between the scratchpad memory and the DRAM. In addition, beyond the NPU core, there are resources shared across multiple cores, such as the on-chip interconnect and off-chip interconnect and DRAM memory controller. And the latency for accessing these shared resources can vary depending on the behavior of different cores. So this dynamic behavior has to be modeled accurately for accurate evaluation of the designs. So far, I focused on the hardware aspect, but in addition, the compiler can have a significant impact on the overall system performance. So modern ML frameworks support compilation capability, and its job is to take the AI models, like the PyTorch or TensorFlow models, and progressively translate them into lower level representations until you arrive at the target machine code binary. And in addition, to support training, they need to perform auto differentiation to generate the computational graph for the backward pass without requiring huge amount of human effort. Also, during the lowering processes, they apply various optimizations, such as operation fusion. So for example, a gem operation followed by a ReLU operation can be fused as a single operation to reduce the DRAM access traffic and the execution time. So this chart is showing the performance impact of compiler optimization by PyTorch on NVIDIA A100 GPU. And as you can see, the difference is quite significant, ranging from 30% to nearly 80%. So such optimization techniques have to be accurately modeled. But for realistic compiler support, it is essential to have an NPU ISA that is well defined to model the behavior of actual NPUs. However, one challenge in adopting an NPU ISA is that there's no de facto standard ISA for NPUs, unlike CPUs or GPUs. So for CPUs, there are well-established ISAs like x86, ARM ISA, as well as RISC-V. And for GPUs, there are ISAs from NVIDIA and AMD that are widely adopted by many hardwares. However, since NPU is relatively new and it is evolving rapidly, there is no well-established de facto standard ISA for NPUs. So we had to address this gap, and we realized that RISC-V can be a strong candidate for this purpose. It is a general-purpose ISA with rich scalar and vector instructions, and it is flexible in terms of supporting different vector lengths. So unlike other vector extensions like Intel AVX or NVIDIA PTX, the vector length of RISC-V can be chosen with greater freedom. So this allows us to explore many diverse NPU architectures compared to using different vector extensions. In addition, there are useful extensions like Physics or vector coprocessor interface extension, which can be used to model the interface between the data flow unit and other units within the NPU core. Also, there are sufficient reserved opcode space, such that custom instructions can be implemented to support functionality required by MPU. And because this is an open ISA, there's no IP restrictions in using this from both academia and industry. And although this is a relatively new ISA, it already has a rich software ecosystem, including the compiler infrastructure and simulators. So it can be a good choice for designing an MPU model. So to address this gap, we proposed PyTorchSim, which was presented in Micro last year. So PyTorchSim is not just an MPU simulator. It is a simulation framework that is integrated with an AI framework called PyTorch. So because it is directly integrated with PyTorch, we can run existing PyTorch models without requiring human efforts to convert them into custom models, model format required by the simulator. In addition, as we implement the compiler backend for PyTorch compiler, we enable accurately modeling the compiler optimizations for the AI models. And we modeled a RISC-V-based MPU ISA that can perform many operations required by modern AI models. And our MPU simulator has a general and extensible architecture, so it can be used to model diverse MPU architectures while still providing fast and accurate simulation capability. But why is it based on PyTorch? So different frameworks have pros and cons, but when it comes to developing new AI models, PyTorch is the most popular choice. So as you can see on the plot, the PyTorch shown in the red portion dominates the choice of the AI framework in AI research. Other frameworks like TensorFlow has been known to be more suitable for deployment at larger scale. However, because PyTorch is widely used by AI researchers, basing the simulation framework on PyTorch makes it easy to support many state-of-the-art AI models without additional human effort. In addition, while early versions of PyTorch lacked compiler support, the compiler support has been added since PyTorch 2.0 for several years now. And when it comes to the MPU architecture, we use the Google TPU architecture as the base architecture. Google TPU is among the most successful MPU architecture that has been deployed in data centers at large scale. It has been matured for more than 10 years and is currently at the 8th generation. Also, many architectural details of TPUs are available in different papers and talks and patents. So it is relatively easy to model their details in the architecture compared to other MPUs that do not reveal much details of the architecture. In addition, the TPUs are available on the Google Cloud for accuracy validation. That is not the case for many other MPUs. So this is very useful for validating the accuracy of the simulation. And while this is a MPU design, it has many similarities with other MPUs from other companies like Intel and AWS by incorporating systolic arrays, vector and scalar units, as well as scratchpad memory and DME engines. Thus, we used Google TPU as the base architecture, but enable modeling other MPU architectures by extension. So our MPU model has these components: the DMA engine and scratchpad memory, scalar and vector units for computation. And in addition to accelerate matrix multiply operations, we adopt data flow unit such as systolic array. And to support transcendental functions and trigonometric functions, we also add a special function unit. And these units perform the operations of the different instructions in the MPU ISA, which is our customized RISC-V ISA with vector extension. And also to support wide data path between the data flow unit and the vector unit, we adopt V6 or vector coprocessor interface extension from Sci-Fi. I will go into more detail on this later. As I mentioned earlier, our MPU ISA is based on a customized RISC-V. So it has many scalar and vector instructions needed for modeling AI operations. It is open ISA, so any company or any university can use it. And it has vector length agnostic vector unit. So different vector lengths can be explored by the MPU architect. And we also add complex custom instructions in the ISA. So it is not necessarily a pure RISC-style ISA. However, one challenge in using RISC-V for MPU in modeling Google TPU is that they have very different ISA. So Google TPU uses custom VLIW ISA. And as many of you know, VLIW stands for very long instruction word. So in case of Google TPU, they use 322-bit VLIW instruction bundle, which includes 2 scalar slots for vector slots, 2 matrix slots, as well as other fields. So there is a significant difference between this ISA and the RISC-V ISA, even if it's customized. So we had to address this gap. And our choice is using a wide but in order superscalar pipeline to model the VLIW pipeline. Of course, this is very different from a real VLIW pipeline. However, the major difference comes from the circuit level complexity, which is not the target for our model. So we are not trying to model the circuit level complexity. Modeling such complexity would require designing an RTL model and synthesizing and routing them to accurately model the area and power cost. However, that is beyond the scope of PyTorchSim, and we focus on accurately modeling the performance. And it turns out that this is good enough to model the behavior of TPUs for many workloads. And since RISC-V has a mature and growing software ecosystem, we leverage them in our project. So we use the compiler infrastructure for RISC-V, such as MLIR and LLVM. And we also adopt simulators for RISC-V architecture, such as Gen5 and Spike. At first glance, RISC-V may not seem like a good fit for MPU ISA. However, in reality, RISC-V has been adopted by many different MPU designs. So for example, Esperanto Technology, Meta, and Semi-Dynamics adopted RISC-V ISA for their MPUs. Let's talk more about the extensions for RISC-V. So I briefly mentioned that we adopt V6 for the interface between the vector unit and the data flow unit. So this is an interface, wide interface that can provide vector data directly from the vector unit, such as vector register file, to the data flow unit. And this is useful because data flow unit require wide interface to take many input data at once and produce many output data at once as well. So we use this interface to provide inputs to the data flow unit. So one input would be the input activation tensor, the other would be weight tensor, and the resulting output will be provided back to the vector unit through this interface as well. So by adopting this, we can provide a sufficiently wide interface between the data flow unit and other parts of the MPU core. So this figure shows how we model the Google TPU core. So on the right, you can see the systolic array, and they are connected to the vector units through V6, as well as the serializers and deserializers. So the push instruction takes the data from vector register file and provide it to the systolic array through the serializers. So this is used for providing input activation tile and the weight tiles. And the outputs are taken by the vector unit using the pop instructions. So a pop instruction takes data from systolic array and the deserializer to the vector unit. And using this can be supported by the RISC-V extension for V6 that is already developed by Sci5. And we use the MLIR's V6 dialect, which is also already available. And we model this interface in our Gen5 core model. However, PyTorchSim is not necessarily limited to modeling just Google TPU, and it can be extended to model other MPU architectures. And there are 2 choices in doing this. So this diagram is showing the earlier design, but with the rearranged components in the core. So the first choice for extending this model to model other MPU architectures is replacing the data flow unit with something else other than the systolic array. So If you want to do this, you need to modify the Gen 5 core model to model your own data flow unit, and also modify the compiler to properly generate the instruction to use your own unit. The second approach is replacing the entire core model with some other core model. So it doesn't necessarily have to be a Gen 5 core model. You can use any other cycle-level core model. And in our paper, we show a case study in exploiting the sparse matrix multiply unit from the Flexagon work to model a heterogeneous MPU core with sparse unit as well as dense matrix multiply unit. So PyTorchSim can be extended in different ways. So far, I focused on the hardware aspect. Going into the compiler aspect, we extend the PyTorch compiler by providing our own backend for the MPU. The way the PyTorch compiler works is, first, the Torch Dynamo takes the AI model described in the PyTorch operations and captures a FX graph, which is the computational graph for the AI model. And to support training, the AutoGrad performs automatic differentiation to generate the backward pass computational graph. And then the Torch inductor takes that computational graph and applies target-independent optimizations that are shared across different MPU architectures, or MPU architectures, or CPU or GPU. Then it will convert that computational graph into loop-level IR. And this is where our MPU backend comes in. So it takes the loop-level IR and translates that into RISC-V binary for our MPU through compilation passes in the MLIR and LLVM. And along the compilation process, we also apply target-specific optimizations for our MPU. So this compiled binary can then be executed on the MPU simulator, one instruction at a time. However, simulating every instruction one at a time can be very slow. Even a simple jam operation can turn into hundreds of instructions for DMA operations as well as the actual computation. So because we wanted to achieve high simulation speed, we had to overcome this challenge of executing so many instructions for accurate modeling. However, we were able to speed up simulation based on a key insight. The key insight here is that MPU cores tend to perform operations using data in the scratchpad memory. And the data movement between the scratchpad memory and the DRAM is managed explicitly by the software using DMA operations. So once the data are available in the scratchpad memory, the compute latency inside the core has no interference from other cores' operation, so the latency of the computation can be obtained deterministically. In contrast, the latency for accessing data from DRAM goes through the shared resources like the one-chip interconnect and memory controller. So this latency cannot be determined in advance, and it has to be modeled dynamically. However, by exploiting the observation that the intra-core latency is deterministic, we can model the compute latency accurately without always executing all the instructions in the binary one at a time. So for example, let's assume a simple systolic array, which is a weight stationary systolic array in this case. And also let's assume that the data are available in the scratchpad memory. The way the systolic array works is you preload the weight tile from the scratchpad memory to the systolic array, and then push input activation tiles from the scratchpad memory to the systolic array. Then after a number of cycles, the result will be available from the systolic array, and you can write it back to the scratchpad memory. But all these latencies can be modeled in advance statically. So the latency for accessing the scratchpad memory can be obtained offline. And in addition, the latency for systolic array compute operation can also be obtained deterministically based on the dimensions of the input tiles as well as the systolic array itself. Furthermore, while there are scalar and vector operations that are fused together with the jam operation, these also use operands from the scratchpad memory, so they can also be statically obtained and reused over time. So instead of simulating all these instructions from the binary every time, we can turn this into a dependency graph modeling different operations. And things like DMA load can become one node, and the matrix multiply computation, as well as other things fused with it, can also be modeled as a single node in the graph. And we can have edges denoting the dependencies between different operations. So if we obtain the compute latency offline, we can reuse it over and over again in order to achieve high simulation speed. And the tile operation graph can include other things like the beginning and end of the loop, as well as the condition to check the number of iterations needed for the AI model. So we refer to this simulation methodology as tile-level simulation, or TLS. So this works in a two-step flow. First, the compute latency is obtained offline using Gen 5 core model. And we obtain the tile operation graph through the compilation process, and we use it during the simulation time. Other things like the DMA operation have non-deterministic latency because of the contention with other cores. So we model them during the runtime in the simulation. And to properly generate the addresses from for the DMA operations, we record the memory access pattern in the tile operation graph and use it during simulation. And the shared resources like the NOC and the DRAM are cycle-accurately modeled by using simulators such as PyTorchSim and Remulator 2. So by applying this method, TLS can achieve both high simulation speed and high accuracy. And as I mentioned earlier, the TOG can be obtained during the compilation process. So I'm revisiting the compilation process. So first, the AI model is turned into an FX graph, which is the computational graph. And then AutoGrad performs automatic differentiation to obtain the backward pass graph. And Inductor performs target-independent optimization and generates loop-level IR. And now this can go into different backends for NPU, GPU, or CPU. In our case, we use MLIR to implement the compiler backend. So as you can see here on the left-hand side code, we express operations such as DMA operation and matrix multiply operation using MLIR. And multiple MLIR passes are used to progressively lower this into lower level representation. And on the right, you can see how the higher level MLIR is turned into lower level operations, such as the custom instructions for the DMA operation, denoted as MVIN, as well as matrix multiplication performed using the physics dialect of MLIR. Then this will be turned into machine code by the LLVM and CLang. And in addition, we perform loop analysis to generate the tile operation graph I mentioned earlier. But not every operation goes through this compilation process using the inductor. So many different platforms use template kernels to model operations such as matrix multiply and convolution. So in PyTorch, the Triton kernel templates are used to implement the matrix multiply operation. And similarly, we use an MLIR kernel template to implement the matrix multiplication and convolution. So at the high level, our NPU compiler backend takes the computational graph expressed in loop level IR, lower them through MLIR and LLVM to generate RISC-V binary as well as TOG. Then this RISC-V binary will be executed offline using Gen 5 to obtain the compute latency, and the latency will be embedded in the TOG for simulation on our simulator called TOG simulator. So the PyTorchSim models the timing aspect of the AI model executed on the NPU. However, one challenge is that when the timing behavior is dependent on the data values, we cannot model the latency as a single constant latency. So for example, consider a matrix multiply, but with sparse input tiles. Depending on the sparsity pattern of the input tiles, the sparsity pattern of the output tiles also can vary. And if the compute unit can exploit the sparsity, the latency of the operation can also vary depending on the input type. So we cannot model the compute latency as a single constant latency. However, one critical observation here is that for a specific pair of input tiles, the latency is still deterministic. So for example, for tile A0 and tile B0, the latency will be x0. And although this latency x0 is different from latency for other pair of input tiles, that latency is deterministic when you are using the tile A0 and tile B0. So although we don't have a single global latency for all the latencies for different tiles, we can still obtain all these latencies offline, and they will be deterministic for that specific pair of input tiles. So we exploit this fact to speed up simulation, even if there is data-dependent timing behavior. We refer to these as data-dependent attributes. So in our simulation framework, we use the Spike functional RISC-V simulator to take the RISC-V binary and the input tensors from the PyTorch runtime to compute the data-dependent attributes. And it can be used along with the TOG to model the timing behavior of the AI model. So after obtaining the TOG and the data-dependent attributes offline, you can reuse this over and over again across multiple simulations to amortize the cost of obtaining the information and achieve fast simulation speed. Yes, questions? Yes.
So can you explain the basic terms of from the PyTorch runtime? So if I understand correctly, so this is still a dynamic runtime, right?
Right.
So do you do an ahead of time export for the IR? So can you kind of explain like how does PyTorch runtime kind of connect to the RISC-V binary? Because the runtime, I would expect this runs on x86 hardware, right? So this is not file for RISC-V.
Right. Yeah. So the compilation process happens dynamically when you use PyTorch runtime to execute the model. Okay. So when you start executing the AI model for inference or training, it'll start the compilation process, and we can then generate the binary and the TOG. So as long as you're executing operation that is already compiled, you can use the TOG that you have generated earlier. If you encounter new operation for which you don't have the TOG already, the framework will go through the compilation process to generate the TOG and other things needed to perform simulation. So yeah, although I said this is offline, in that sense, it's dynamic. Okay, compilation process is dynamic. And in addition, the Spike functional model can be used to obtain the output tensors from the MPU that is being modeled. So you can compare the output tensors from our simulation framework with the tensors from actual devices like CPUs and GPUs to validate the correctness, functional correctness of the simulation framework, including the compiler and the functional model, the Spike itself. So putting it all together, we implement a MPU backend for our MPU model using MLIR and LLVM to generate RISC-V binary and TOG, as well as data-dependent attributes using Gen 5 and Spike simulators. And then the resulting TOG and the data-dependent attributes will be used by PyTorchSim to model the timing aspect of the MPU accurately while achieving fast speed. So this is comparing the feature of PyTorchSim to other simulators or analytical models. So different rows are corresponding to different tools, and each column is corresponding to a feature. And as you can see, PyTorchSim can provide high speed as well as multi-core, multi-tenancy modeling capability. And we model DRAM and interconnect cycle accurately while supporting general effective operations through compiler. We also support training. Our architecture is based on RISC-V, and we can model data-dependent timing model. And again, it is based on PyTorch, so you don't need to modify existing PyTorch model to run them on the simulator. If you are curious about the details, please refer to our paper. So with that, I will present some evaluation results. Our validation target is Google TPU v3, which was the most recent TPU version with sufficient details available at the time of development. We compare against different simulators and the analytical timing models using this configuration in the table. For simulation speed comparison, we only compared against cycle accurate simulators because obviously analytical models are way faster than PyTorchSim, although they don't provide very accurate results. So we use XLSim and MMPuSim for speed comparison. The XLSim is a GPU simulator, but we used it for comparison because GPUs are widely used for deep learning, and it has rich features that are not available in other simulators. And in terms of workloads, we looked at individual kernels as well as full AI models. So this is showing the accuracy of different simulators against real TPU v3. So on the x-axis, we have different workloads, and on the y-axis, we have the relative error. So numbers closer to 0 are better. And as you can see, PyTorchSim achieves better accuracy than other tools, achieving a mean absolute error of 12%. The accuracy benefits mainly come from properly modeling the vector operations. So vector operations are not well modeled by other tools, and they tend to underestimate the full model runtime because they don't support vector operations properly. So PyTorchSim can accurately simulate the full models end-to-end. In terms of the simulation speed, we are plotting the simulation speed of PyTorchSim and other simulators normalized to that of the XLSim. So compared to XLSim, we can achieve 48 times speed up overall. And the high-level simulation enabled 9x speed up compared to PyTorchSim running in the instruction level simulation mode. And compared to MMPuSim, we can still achieve 7.4x speed up. So we can provide significant speed ups compared to other simulators. There are several case studies available in our paper. So if you're curious, please take a look at the paper. PyTorchSim is not a perfect tool. So there are many missing features and many ways to further improve it to make it more useful for various different scenarios. So one thing to consider is extending it to support other frameworks such as TensorFlow and JAX. And because GPUs are becoming more and more similar to NPUs these days, I think it might be possible to model deep learning performance on GPUs with this approach. And the NPU kernel time can be used in larger scale simulation tools such as LLM serving sim and retrain to model the larger scale inference and training performance. And we are actively working on implementing missing features of PyTorchSim to make it more useful. So to summarize, NPU system research requires a comprehensive, fast, and accurate simulator. We propose PyTorchSim to enable high-speed, high-accuracy simulation through tile-level simulation. It is integrated with PyTorch2 compilation flow, and it has a generic and extensible architecture for RISC-V-based NPU model. And compared to other NPU simulators, we can enable more diverse case studies while improving accuracy and simulation speed. As you know, PyTorchSim is open source. Contributions are welcome. And last night, we updated the PyTorchSim to 1.1 with non-trivial changes. So yeah, we are working on improving it, and I hope you can use it for your own research. That is it. Any questions?